Hello there, my name is Kevin Cunningham, and today I'm going to be talking to you a little bit about my final year theoretical physics project called Black Hole Shadows and Ray Tracing, which I did under the supervision of Dr. Niels Warburton. The purpose of this project was to produce a piece of software which would render physically accurate images of spinning and non-spinning black holes with and without accretion disks. Towards the end of the project, I decided to extend the software to render images of Majumdar-Papapetrou static binaries. And ray tracing is a method commonly used in the film and video game industries. It involves tracing the path of a beam of light backwards in time to its source, and by doing that, we know what color the light should be. Now, because in our everyday experience, light travels in a straight line, we can usually do this using Euclidean geometry. But in the presence of a strong gravitational field, light will no longer travel in a straight line, so this method is no longer valid. Now, Euclidean geometry doesn't hold in the curved spacetime near a black hole. This curvature can be described by a line element, like the one we see here. In particular, this line element describes a static, stationary, spherically symmetrical spacetime. From line elements like this, we can find differential equations known as geodesic equations, and by numerically solving these, we can find the path or the geodesic that a particular photon follows. If we integrate far enough backwards, we can find the origin of the light, and by doing that, we know what color it should be. So on the previous slide, I introduced the idea of a line element, and I said that we can use this to derive the geodesic equations, and that's what I did for each of the spacetimes that we'll see later on in the presentation. In order to relate the initial conditions of each geodesic to the direction that a ray of light approaches our observer at, I used an inner product like we see here. So this is the same concept as taking a dot product in Euclidean space. Here, G is our metric, encodes the same information about curvature that the line element does, but this little symbol here, I'm using to denote the fact that this is the part of the metric orthogonal to the time direction, so it's the spatial part of the metric. I then wrote a Mathematica notebook, which uses the ND-solve function to numerically solve the geodesic equations, and uses the image transformation function to apply these to the image that we're going to see. Now this code took an awful long time to run, even for very low resolution images. So I later parallelized the code, meaning I could run it over multiple cores at the same time, and I wrote it as a script which I could run remotely on a big 40-core computer. So all the ray diagrams and the black hole renders you're going to see in this presentation were made by myself, either on my laptop or on that big 40-core computer. The Schwarzschild black hole represents the spherically symmetric stationary and static solution to the Einstein field equations. The spherical symmetry of the system means that our geodesics will remain in one plane, while the choice of equatorial plane is arbitrary, which is great because our equations simplify the equatorial plane. So overall, this means that we can describe any geodesic with these simplified equations, which makes our calculations a lot more efficient. Here we have a few examples of geodesics a photon can follow in Schwarzschild spacetime. So before we look at any in particular, this black dashed circle around represents our celestial sky, so kind of the background sky, and in our calculations we take it as being asymptotically far away. So in this first diagram here, we can see a geodesic which is only slightly curved. In our second diagram, we can see a more curved geodesic to the point where an observer can see an object behind a black hole. Diagram C is again more dramatic. An observer looks to the right of the black hole, but they see an image from off to the left of the black hole. Now, normally in our everyday experience, when we look at something, we expect that we're seeing the front of it. Image D here shows that with black holes, that's not quite true. As we look at a black hole, we see not just the front of it, we can also see the sides of it, and indeed the back of it. In figure E, this deflection is more pronounced again. So an observer looks to the side of the black hole and they see light that comes from themselves or from behind them. Figure F, again, is a more pronounced deflection. Light comes in, does a loop around the black hole before making it to our observer. In principle, light can do an arbitrary number of loops before escaping its loops and going to an observer. Now this is one of the first images I was able to render. This is a Schwarzschild black hole in front of a coloured grid. Off to the sides, we can see the grid lines aren't massively affected, because the light hasn't traveled close enough to the black hole to be strongly deflected. Closer to the black hole, we see this ring. This is what's known as an Einstein ring, and it occurs when light from an object directly opposite us on the far side of the black hole gets deflected to us from all directions. This is similar to what we saw in figure B before. This yellow patch here is a reflection of this yellow patch, where as we look here, we see light that has been deflected from over here. And if we look a little bit closer to the black hole again, we can see a narrow red sliver, which corresponds to light which has done a loop around the black hole before it comes to us, like we saw in figure F before. The black hole shadow here is a circle, which we expect because of the spherical symmetry of the system. The middle of this circle represents the front of the black hole. A little bit off to the side is the side of the black hole, and the edges of this black disk will be the back of the black hole. Here we see our black hole in front of a starry background. This is interesting to look at because we can see the reflection of individual points. So for example, this star here is reflected here inside the Einstein ring. This star here is reflected from here, and these two stars are a reflection of these two stars here. Now, if we were to sit just outside the black hole, all we would be able to see in most directions is the event horizon, which is this black around here. If we look in one specific direction, we'll be able to see some light coming from the sky. And in fact, this light is coming from the sky in every direction around the black hole. So in this one circle, we can see the entirety of the universe. The Kerr black hole is the next step up from a Schwarzschild black hole, in that it has some angular momentum, so there's some spinning going on. This is generally what we expect of bodies in space. And indeed, measurements have been taken which show that even supermassive black holes can have nearly the maximum spin we think is physically possible. Now, we don't have spherical symmetry anymore because the spin axis of the Kerr black hole provides a preferred direction. So we're no longer going to have geodesics being staying in the plane, and we can no longer arbitrarily choose our equatorial plane. As well as that, our black hole shadow will no longer be symmetric. So our geodesics in Kerr spacetime are going to look a little bit different. So for light traveling prograde with respect to the black hole, so traveling in the same direction as the black hole spin, it can get a little boost as it travels past. On the other hand, if light is traveling retrograde, so against the spin, if it gets too close to the black hole, it's going to be forced to change direction to travel in the same direction as the spin. So for an observer sitting above a black hole, light will come in from the sky below the black hole. As it bends up around the top of the black hole to our observer, it does a little twist, as you can see here. This is different to what we would expect in the Schwarzschild case, where it should have stayed in the plane. And we have another geodesic here, just to show that these geodesics are now 3D, they move out of the plane. Here we can see a Kerr black hole in front of the same colored grid that we used earlier on for the Schwarzschild black hole. Here our observer is sitting in the equatorial plane, and we can still see the same Einstein ring we saw earlier on. We can still see the same reflection of colors, although it's not as symmetrical as it was earlier on. One of the more interesting features is along the side of the black hole shadow here, we see flattening. This corresponds to light traveling prograde with respect to black hole spin, so getting a little boost, which means that we're going to be seeing light coming from that direction that we wouldn't have been able to see in the Schwarzschild case. Similarly, the right-hand side of the black hole shadow is going to be a bit extended because light that wanted to come from that direction will be traveling retrograde with respect to black hole spin. And as we saw earlier, that's going to be slowed down and blocked. Here is an image of a Kerr black hole as seen by an observer sitting on the rotation axis above the black hole. The reason this grid is a lot more colorful is because I find a finer grid works to demonstrate this effect a lot better. We can see the kind of twisted pattern in the background. That corresponds to the image we saw earlier on of light twisting as it comes up from below the black hole to an observer sitting above the black hole. Now the short animation here corresponds to what a slowly moving observer might see as they move from the equator to the pole of a Kerr black hole. Now black holes aren't expected to be found in a vacuum in nature. They're expected to be surrounded by clouds of gas and dust. And this has been seen by the Event Horizon Telescope last year. Now, these clouds of gas and dust can be modelled using general relativistic magnetohydrodynamics, but that is beyond the scope of this project. So we've been modeling accretion disks as flat annuli in the equatorial plane. Here we have a few ray diagrams for a Schwarzschild black hole with an accretion disk. In the first image, we can see that the light travels in almost a straight line, which makes sense since the light isn't traveling close enough to the black hole to be significantly deflected. In the second image, we can see the light from the top of the back of the accretion disk will be deflected towards our observer. So we would expect to see an image of the accretion disk someplace here. In figure C, we see that similarly light from the bottom of the back of the accretion disk will be deflected towards our observer, so we'll expect to see an image of that someplace here. In figure D, we see that the observer can even see the bottom of the front of the accretion disk, although this will appear as a very narrow band above the black hole. So here we see a Schwarzschild black hole with its accretion disk. For clarity, the top of the black hole is colored blue and the bottom is colored red. So we can see the entire top of the accretion disk, as we'd expect from the previous slide. And we can see most of the bottom of the accretion disk, again, as we expect. Now, this animation is a sped up version of what a slowly moving observer would see if they orbited around the black hole from the previous slide. Here we can see a Kara black hole with its accretion disk. So the disk was initially modeled as having 6 colored segments of equal size. We can see that towards the front, this looks like it's carried over, but towards the back, the green segment is extended while the yellow segment is squashed. This corresponds to light from the green segment traveling this way around the black hole, so coming prograde towards us and getting the boost that we talked about earlier, whereas light from the yellow segment can't do the same because it is traveling retrograde if it tries to. Again, this animation corresponds to sped up footage of what a slowly moving observer would see as they orbit around the black hole from the previous frame. Now, moving on from individual black holes, black hole binaries have long been theorized, but they were only recently proven to exist with the first measurements of gravitational waves. These black hole binaries are incredibly complex and dynamical, and they're normally modeled using numerical relativity or perturbation theory. Both of these theories are beyond the scope of this project, so I've used a toy model known as the Majumdar-Papapetrou static black hole binary. In this model, black holes have enough charge to balance their gravitational attraction. These aren't very physically realistic systems, but they do allow us to observe some of the characteristic features of binary, at least at a qualitative level. Here we see ray diagrams for the Majumdar-Papapetrou spacetime. In the first diagram, we can see that the observer can clearly see one of the black holes. In the second diagram, we can see that the observer will see the partner black hole further to the side of the first black hole. The observer will also see an image of the first black hole even further to the side. And this will be a repeating pattern where the observer can see images of each black hole alternating between the first and the second. In the final diagram here, we see the observer aligned with the two black holes. Clearly, the observer will be able to see the black hole closest to him, but he will also be able to see the black hole behind that. So here's an image of our Majumdar-Papapetrou black holes in front of the same colored grid from earlier on. Again, we can see an Einstein ring around the outside, and as we look in, we can still see the reflections off to either side. But as we look closer, we see our pair of black holes, and we see the images of each that we expect to see from the ray diagrams we saw earlier on. If we zoom in closer, we can see that here we have our primary black hole on the left. Here we have the first image of the black hole from the right. Here we have another image of this first black hole again. And if we were able to zoom in further and further, we'll see that this pattern repeats itself. We can also see here inside the first black hole, there will also be an image of the partner black hole. Finally, we have an image from an observer aligned with the two black holes. We can see, as we'd expect, the closer black hole in front. There's a gap where light can get through. Then behind that, we can see an Einstein ring made up of the black hole further away. And again, we can see that this pattern is going to repeat. We're going to have repeated images of each black hole. Finally, I have a short list of references just covering what I've talked about today. I hope you've enjoyed listening, and if there are any questions, please don't hesitate to let me know.